Ms.K.MANIKKILI. I am an assistant professor of the mathematics department. I am going to handle ordinary differential equations. So before we are going to see ordinary differential equations, first of all we should know what is a differential equations. Differential equations are nothing that it is a mathematical equations that relates their functions and also its derivatives. It means it expresses how a quantity changes with respect to the another variable, typically named time and also space. So formally, so differential equations involves unknown functions, so y of x and its derivatives such as f of x comma y dash y double dash and so on, y power n equal to 0. So according to this case here, so x is a independent variable and y is a dependent variable. Y dash, y double dash, y triple dash and so on. So y power n is also a first and second and third derivatives of this y. So here is y is a function that defines all those relationships. So next we are going to see what is a type of differential equations. Differential equations has two categories. One is ordinary differential equations, another one is a partial differential equations. Ordinary differential equations nothing that involves only one independent variables and the derivatives. For example, this is a time. Okay, so ordinary differential equations we are going to write like that. dy by dx is equal to y for here. Here, so y is depending on x. X is here is independent variables. So partial differential equations are nothing that involves multiple independent variables and also partial derivatives. For example, space and also the time. So partial differential equations we are going to write like that only. Dou u by dou t equal to c square, dou square u by dou x square. So according to this case here, u is depending on t and also u is depending on x part here. So now we saw what is the types of differential equations. Now we are going to see what is the real world example of the differential equations. So nothing that. So first one here is mentioning the population's growth and second one is a bank interest, third one is a cooling of parking. Both all those things is depending on only the time durations. Here, so everything is independent variables. Dependent variables depending on is only the time. Time is here is independent for here. So next we are going to see what is the definition of linear differential equations. Linear differential equations are nothing that is one in which the dependent variables and its derivatives occur with the first degree and there is no product of dependent variables and derivatives of the product of derivatives. For examples here, so x into d square y by dx square plus y is equal to x square is a linear equation because here, so y is only one independent variable, dependent variables and x is for here is independent variables. Y is again I am repeating, y is here depending on x. There is only one dependent variables is occurring here. So because of reasons we are saying it is a linear differential equations. And also differential equations which not in linear is called as a non-linear differential equation. That means for example here y into dy by dx plus x square equal to 0 for here. So it is an example for as a non-linear differential equations. So next we are going to see, so whenever the linear differential equations with constant coefficients given, how to find our solution for that one. Okay, so in general form is given here a naught b power n y by dx power n plus a1 dn minus 1 y by dx power n minus 1 and so on like that equal to q of x. Here a naught, a1, a2, a3 and so on, an minus 1, an are constant. And also here, so a naught is always not equal to 0. And if q of x equal to 0, that means equations 1 it will come like that only. So equations 2 is called as a homogeneous equations. That means here equation is, that means this equations whenever equal to 0, that equations is called as a homogeneous equations. Now we are going to find a solution of this linear differential equations. So our general solution is always in the form y is equal to yc plus is a yp. So yc is a nothing that is a complementary function and yp is a nothing that is a particular integral. Okay, So both are including, we are saying that this y is called as a complete solution. So next we are going to find how to find our complementary functions. Okay, so whenever d is equal to dy by dx, we know very well this is the first derivative. D square is equal to d square by dx square, it is a second derivative. D cube is equal to dq by dx cube, it is a third derivative. So and so on. D power n is equal to d power n divided by dx power n. This is our nth derivative. So we are going to rewrite our equations 1. So equations 1 is here. Equations 1 is here. Okay, a naught d power n by dy by dx power n and so on here equal to the q of x. We are going to rewrite the equations here. So a naught d power n plus a1 d power n minus 1 equal to the q of x. Now we are going to find our complete function. That means this equation is equal to 0. Replacing d by m in equation 4, we get the equation is in this form. That means our whatever in our left hand side, that portion is equal to 0 from here. Here m1, m2, m3 and so on, m1 are roots of equations 5. This equation is called an auxiliary equations. If 4 cases are arising here, so case 1, case 2, case 3 and also so case 4. What is the case 1 for here? So all the roots are real and also so different means we are going to write our complementary functions in this way only. C1 e power m1x plus C2 e power m2x plus and so on Cn m power e power mnx for here. Second case is all the roots are, that means real at the same time equal means we are saying here m1 equal to m2 equal to m3 and so on, so m1 equal to, we are saying is a common form here. Okay, so then we are going to write our complementary functions in this way only. And third case is, so roots are is equal. Whenever, in second case only, the two roots are equals and same times we are going to write our complementary functions in this way only. And third case is like that, two roots are complex, that means m1 equal to, we know very well, so m1 is the one of the root and m2 is also another root for here. m1 is equal to alpha plus I beta, this is a complex solution. That means alpha is a real number and beta is also a real number. So another root is alpha minus I beta, so alpha is again is a real number, so beta is also a real number. So both roots are is a complex roots. Whenever the complex roots is occurring at the same time that the another roots are is a real means we are going to write our complex complementary functions in this way only. And fourth case is both roots are is equal, that means both complex roots are is equal means look like that m1 equal to m3 is equal to this one and m2 is equal to m4 equal to, and this one means we are going to write our complementary functions in this way only. So see here this form only. So next we are going to see how to find our particular integral. Next we are going to find our particular integrals. Whenever that q of x, that means whatever in our right hand side. Okay, so q of x is equal to e power x means, okay, first type of problem. We are going to find our particular integral dA is equal to 1 divided by f of d into e power a. This f of d is nothing that whatever they have given our differential form. Okay, so this we are going to rewrite. That means we are going to substitute b equal to the coefficients of a means, so f of a not equal to 0, then particular integral it will come look like that b power ax divided by f of a. Here we are replacing d is equal to a for here. So in second case, if f of a equal to 0, that means the denominator is going to be 0, so that time our f of t it will come to look like that, not like that means our denominator we are going to differentiations one more time, at the same time we are going to multiplications x in our